The night sky is a beautiful lie. We gaze up at a canvas of stars, completely unaware that almost everything is hidden from our view. The cosmos is filled with unseen corners and cosmic discoveries that defy logic, from ghostly gravitational pulls to cosmic structures that should not exist by any known law of physics. By the end of this journey, you will see the universe not as a static picture, but as a living, breathing puzzle box of the unexplained. We will confront a star that flickers as if something colossal is blocking its light, and a mysterious force tugging our entire galaxy toward an unseen horizon. What part of reality do you think is still hiding in plain sight? There is a place in the cosmos so profoundly empty it defies all expectations. We call it the Boötes Void, a name that barely hints at its unsettling nature. Imagine a spherical region of space so vast it could contain thousands of galaxies like our own Milky Way. Yet inside this colossal volume, there are only a handful. It is a cosmic desert on a scale that is almost impossible to comprehend, a great nothing spanning hundreds of millions of light years. Astronomers stumbled upon this emptiness not by looking for nothing, but by meticulously mapping the distribution of galaxies, expecting to find the universe's matter spread in a relatively even cosmic web. Instead, they found a gaping hole. The void's existence challenges our most fundamental models of how the universe evolved after the Big Bang. According to those models, matter should not have clumped together in such a way as to leave a void of this staggering size. It is like finding a single, perfectly spherical bubble the size of a continent in an otherwise foamy sea. Some theorists, like Dr. Laura Mersini-Horton, propose an even more mind-bending explanation. This void might not be a simple absence. It could be a signature, a cosmic fingerprint left by another universe brushing against our own in the multiverse, or perhaps a fossilized imprint of a massive quantum fluctuation from the very birth of reality. The Boötes Void forces us to confront a humbling truth. Emptiness is not passive. It is an active puzzle, a profound silence that asks us what we are truly missing. If such a vast nothing can exist, what other immense absences are waiting in the dark, challenging our understanding of everything? But even a void of nothing is not the strangest pull we feel in the cosmos. Astronomers have detected something far more unsettling, a current flowing through the fabric of space itself. They call it dark flow. Picture hundreds of massive galaxy clusters, each containing thousands of galaxies, all drifting in the same direction. They are not moving apart due to the expansion of the universe. They are being pulled like leaves on a river toward a single point on the horizon. The force required for this coordinated motion is unimaginable, and its source lies beyond everything we can possibly see. This phenomenon was not discovered by looking at the galaxies themselves, but by studying the oldest light in the universe, the cosmic microwave background. This faint afterglow of the Big Bang serves as a cosmic backdrop. As these galaxy clusters move, they leave a subtle imprint on this ancient light, a kind of Doppler shift that reveals their collective velocity. The leader of the team that found this, cosmologist Alexander Kashlinsky, describes it as a flow toward something we cannot observe. The most logical explanation is a gravitational pull, a titanic tug from a concentration of mass so immense it defies belief. But here is the true mystery. This mass cannot be inside our observable universe. If it were, we would see it. This suggests the pull is coming from a region of space-time beyond our cosmic horizon, from a place that light from the Big Bang has not had time to reach. This single idea shatters a fundamental principle of modern cosmology, the assumption that on the largest scales, the universe is smooth and homogeneous. Dark flow screams that it is not. It points to structures that existed before our Big Bang, or perhaps to the gravitational influence of another universe entirely in a vast multiverse. This is not just a new object in the sky. It is evidence that our entire cosmic home is not isolated. We are connected to something greater, a drift in a current whose source we may never find. How do you map a universe when the compass points to a shore you cannot see? This current flowing through the cosmos is invisible, but another signal from the void was so loud and clear it made an astronomer write a single, powerful word in the margin of a data printout. Wow. In the summer of 1977, a radio telescope in Ohio, part of the Search for Extraterrestrial Intelligence project, was listening to the sky. On August 15th, it picked up something extraordinary. For 72 seconds, a narrowband radio signal, the exact type scientists predicted an advanced civilization might use to communicate, blared from the direction of the constellation Sagittarius. It was 30 times stronger than the background noise of space, a perfect, artificial-sounding burst in a universe of natural radio hiss. Astronomer Jerry Amon was reviewing the data days later when he saw the alphanumeric sequence representing the signal's intensity. He circled it and in a moment of pure astonishment wrote, "Wow." That one word scribbled in red pen would name one of the most enduring mysteries in science. The signal was never detected again. For decades, astronomers have pointed their most powerful instruments toward that same patch of sky, listening for a repeat, a follow-up, anything. There has only been silence. The very nature of the WOW signal is what makes it so perplexing. It occupied a single, quiet radio channel, the cosmic equivalent of a whisper in a specific, protected frequency, one that is naturally silent due to the properties of interstellar hydrogen. This is precisely why scientists searching for alien intelligence monitor that frequency. A natural cosmic event would likely have been broader, spread across many frequencies. This was a clean, sharp spike. So what was it? The debate continues to this day. Some suggest it was a comet that was not known at the time, but that explanation fails to satisfy many experts because comets do not produce such intense, narrowband signals. Others propose it was a reflection of a human-made satellite off a piece of space debris, a cosmic echo of our own technology. Yet, no such satellite has ever been conclusively identified as the source. Then there is the most tantalizing possibility that for 1 minute and 12 seconds we intercepted a transmission. Not a deliberate message beamed at Earth, but perhaps a powerful, one-time burst from an alien civilization's own activities, a piece of cosmic machinery turning on, or a beacon sweeping across the galaxy that just happened to point in our direction for a fleeting moment. The signal came and went, a single, perfect note played in the dark. Its legacy is the profound question it leaves behind. Was the WOW signal our first and only brush with another intelligence, a hello we were just too slow to answer, or is the universe simply capable of creating illusions so perfect they tease us with the promise of company? While the WOW signal was a fleeting burst of sound, another mystery shines with a persistent and unsettling light. In the constellation Cygnus, a star named KIC 8462852, but better known as Tabby's star, is doing something that should be impossible. Discovered not by a team of professional astronomers, but by citizen scientists sifting through public data from the Kepler Space Telescope, this star's behavior immediately stood out. It flickers, but these are not the gentle, rhythmic dimmings caused by an orbiting planet. This star's light drops by staggering amounts, sometimes more than 20%, as if something colossal and irregular is moving in front of it. A planet, even a gas giant, would only block about 1% of a star's light. These dips are far too deep and far too chaotic. The star is named for the astronomer who led its initial study, Tabby, who first tried to explain the bizarre light patterns with a swarm of comets, a vast family of icy bodies breaking apart and casting intricate shadows. Yet even that dramatic idea struggles to account for the sheer scale and strangeness of the dimming. When you eliminate the impossible, as the saying goes, whatever remains, however improbable, must be the truth. This line of thinking led to a theory that captured the public imagination: alien megastructures. The idea is that an advanced civilization might build a vast array of energy-collecting panels, a Dyson swarm, encircling their star. Such a colossal, incomplete structure would indeed cause the irregular, deep dimming we observe. It is a breathtaking thought that we might be witnessing the signature of a civilization so advanced it can re-engineer its own sun. Yet the universe is a master of illusion. Subsequent observations have revealed that the star is also dimming over the long term, fading slightly but steadily over years. This complicates the megastructure idea, pointing instead to some intrinsic and poorly understood stellar phenomenon. Perhaps the star is surrounded by a thick, uneven disk of dust and debris from a recently shattered planet. Maybe it possesses a magnetic activity so violent it creates vast, dark starspots that blot out its light. Each new observation rules out one natural explanation while failing to provide a definitive answer. Tabby's star remains an enigma, a cosmic lighthouse flashing an erratic signal we cannot decipher. It challenges not just what we know about stars, but what we believe is possible around them. Are we watching the death throes of a world, the birth of a new type of stellar behavior, or something else entirely, something built not by nature but by intelligence? While we search for answers around a single star, our own galaxy holds a secret on a far grander scale. Two colossal bubbles of energy, each one a towering structure of gamma rays and X-rays, extend for 25,000 light-years above and below the Milky Way's core. Together, they form an hourglass shape 50,000 light-years across, a ghostly monument to a cataclysm we never witnessed. We call them the Fermi Bubbles, discovered only in 2010 by a telescope designed to see the universe's most violent light. For all of human history, these immense structures were invisible, hidden in plain sight just beyond the veil of our own galactic disk. Their symmetry is perfect, their edges surprisingly sharp, as if someone drew two perfect circles in the sky with a cosmic pen. Astrophysicist Douglas Finkbeiner and his team, who first identified them, were faced with a staggering question. What kind of event could possibly create such clean, energetic, and symmetrical structures on a scale that dwarfs entire star systems? The leading suspect is our galaxy's own supermassive black hole, Sagittarius A star. For most of its life, this 4 million solar mass giant is relatively quiet, a sleeping behemoth. But the Fermi Bubbles suggest that millions of years ago it woke up. The theory is a period of intense accretion, a violent feast where vast amounts of gas and dust spiraled into the black hole's maw. This feeding frenzy would have generated unimaginable energy, powering jets of superheated matter that blasted directly out from the galactic poles, punching through the interstellar medium and inflating these colossal bubbles. The energy required is almost beyond comprehension, a burst equivalent to the simultaneous explosion of 100,000 stars. This single event would have reshaped the galactic environment around it. So how did such a powerful eruption occur without utterly devastating the stars and planets in its path, including our own solar system? The answer lies in the direction of the outburst. The jets did not spray out along the crowded galactic plane where most stars, including our Sun, reside. Instead, they shot out perpendicularly from the top and bottom of the black hole's accretion disk, finding the path of least resistance through the thinner halo of gas above and below the galaxy. It was a narrowly focused vertical explosion, a cosmic safety valve that channeled its fury away from us. The Fermi Bubbles are not a static sculpture. They are an ongoing event, still glowing with high-energy radiation, a testament to the violent processes that continue to shape galaxies. They force us to see our galactic home not as a stable, serene island, but as a dynamic and occasionally violent engine. We live in the quiet aftermath of a sleeping giant's last great roar. What other echoes of ancient cataclysms are still ringing through the dark, waiting for us to learn how to listen? The silent, monumental Fermi bubbles are a testament to a past explosion, but our galaxy is caught in a present-day motion, a headlong rush toward an unseen destination. We are all moving, pulled by a force we cannot see. Our entire Milky Way, along with its local group of galaxies, is racing through the cosmos at a staggering speed of over 1 million miles per hour. For decades, astronomers knew we were moving, but the ultimate source of this motion was a profound mystery. The target of this cosmic pilgrimage is known as the Great Attractor, a gravitational anomaly of terrifying scale located in the general direction of the Norma cluster, some 250 million light-years away. Its name evokes a sense of a final, inevitable pull, a siren call from the void. Yet, for a long time, its true nature was completely hidden from our view, lying directly behind the crowded, dusty central plane of our own galaxy. This region of the sky is so thick with stars, gas, and cosmic dust that it is like trying to see a distant city through a dense, permanent fog. This zone of avoidance, as astronomers call it, blocked our view of the Great Attractor for generations, turning it into a ghost in our cosmic maps. How do you study a monster you cannot see? Pioneering astronomers like René Cron-Courtoueg took on the challenge. Using telescopes that see in infrared and radio wavelengths, which can pierce through the obscuring dust, they conducted meticulous surveys of this hidden realm. What they found was not a single, colossal object, but something equally significant, a massive overdensity of galaxies. The Great Attractor is not a point in space, but a vast gravitational focal point, a continent of galaxies whose combined mass creates an immense well in the fabric of space-time. This discovery fundamentally challenges the simplest idea of cosmic expansion, which suggests that on the largest scales, galaxies should be drifting apart from each other in a relatively uniform flow. The Great Attractor proves the universe is far more lumpy and dynamic. Galaxies are not just passively receding, they are actively flowing, caught in rivers of motion, driven by the gravitational pull of the largest structures in the universe. These large-scale flows are thought to be governed by the hidden architecture of dark matter, the invisible scaffolding upon which galaxies are built. The Great Attractor is likely the heart of the Laniakea supercluster, a filamentary web of galaxies that spans 500 million light-years, and our Milky Way is merely a suburb on its outer edges, flowing toward the metropolitan core. The sheer scale of this motion is humbling. We are not stationary observers of the cosmos. We are passengers on a galactic ship, sailing on a current set in motion by the gravitational landscape of the unseen. What immense structure, what cosmic mountain range, truly lies at the center of this pull, dictating the motion of thousands of galaxies for billions of years to come? Our galaxy's grand motion is a slow, cosmic drift, but some visitors pass through in a flash. In October 2017, astronomers in Hawaii detected a point of light moving at impossible speed. It was not from our solar system, For the first time in recorded history, we were witnessing an object from another star. They named it Oumuamua, Hawaiian for a messenger from the distant past. Its trajectory was a hyperbola, a path so fast and steep it could only mean one thing: this traveler was just passing through, a rock from an alien sun. The initial observations were baffling. It had no visible coma, the fuzzy halo of gas and dust that defines a comet. It was dark, reddish, and tumbling through space. But the greatest mystery was its shape. By analyzing how its brightness changed as it rotated, scientists concluded Oumuamua was dramatically elongated, perhaps 10 times longer than it was wide. It resembled a cosmic cigar or a pancake tumbling end over end, a form unlike any asteroid or comet we had ever seen in our own solar system. Then came the true shock. As it sped away from the sun, its trajectory could not be explained by gravity alone. It was accelerating as if pushed by an unseen force. For a comet, this is normal, caused by outgassing, when sunlight vaporizes ice, creating jets that act like tiny thrusters. But Oumuamua showed no signs of outgassing. No gas or dust cloud was detected around it, no icy tail. So what gave it that extra push? This is where the mystery deepened into profound speculation. Harvard astronomer Avi Loeb proposed a radical idea. What if the acceleration was not from outgassing, but from sunlight itself? A solar sail, a thin, lightweight structure pushed by the radiation pressure of starlight, is a technology we are developing ourselves. Loeb suggested Oumuamua could be a piece of discarded alien technology, a derelict light sail from a civilization far away. It was a hypothesis built on the object's strange properties, its unusual shape perfect for sailing, its lack of a coma, and its non-gravitational acceleration. The scientific community largely favors natural explanations. Perhaps it was a shard of a Pluto-like planet from another system, rich in nitrogen ice that vaporized without leaving a visible trail. Or maybe it was a fractal-like aggregate of dust, a cosmic dust bunny with such a low density that sunlight could easily push it. Yet each natural model struggles to explain the full suite of Oumuamua's oddities. Its brief visit left us with more questions than answers, a single day to point from the vast interstellar sea. It was a messenger that delivered one clear, unsettling truth. Our solar system is not an island. We are being visited by pieces of other worlds, and we have only just begun to notice. How many other silent, tumbling travelers are sailing the darkness between the stars, each one a potential key to unlocking the diversity of galactic architecture. Even the echoes of creation hold a strange and unsettling pattern. The oldest light we can see, the cosmic microwave background, is the cooled remnant of the Big Bang itself, a baby picture of the universe. For decades, it has been our best evidence that the cosmos is isotropic, meaning it looks the same in every direction, with no special place and no preferred axis. This is the bedrock cosmological principle, but that picture is now cracking. Deep within the most precise maps of this ancient light, from satellites like Planck, astronomers found an anomaly so unnerving they nicknamed it the axis of evil. It is not a malevolent force, but a pattern, a mysterious alignment where the hot and cold spots in the cosmic microwave background appear to be correlated with the plane of our own solar system. This is deeply troubling. Why would the structure of the entire universe, from its very first moments, care about the orientation of our tiny, insignificant planetary system? It is as if you drew a map of the entire Earth and found that the continents were subtly aligned with the floorboards in your living room. The implication is staggering. It suggests the universe might have a fundamental orientation, a preferred direction that breaks the sacred rule of isotropy. Cosmologist Joe Megiddo and others have wrestled with this. Could it be a statistical fluke, a 1 in 1,000 chance that we just happen to see this alignment from our particular vantage point? Perhaps, but as our maps get more and more precise, the anomaly stubbornly refuses to go away. The other, more profound possibility is that we are seeing evidence of new physics. Maybe the universe is not perfectly uniform. Perhaps it has a large-scale rotation we never suspected, or its expansion is slightly different in one direction than another. Some even speculate it could be a fingerprint from a time before the Big Bang, a scar from a collision with another universe that imprinted a direction onto our own. The axis of evil is not an object in the sky, but a flaw in our fundamental map of reality. It whispers that our most basic assumption about the cosmos, that it has no center and no edge, might be incomplete. What if the universe is not a featureless expanse, but has a grain to it like cosmic wood, and we are only now learning how to feel its texture? The axis of evil challenges our most basic map of reality, but there is another, even more pervasive ghost in the cosmic machine. It is a substance that outnumbers the stuff we are made of by a factor of 5 to 1, an invisible presence that holds the entire universe together. We call it dark matter. Its story begins not in the vast emptiness between galaxies, but within the whirling dance of a single spiral galaxy. In the 1970s, astronomer Vera Rubin was meticulously measuring how fast stars orbit the centers of galaxies. According to the laws of gravity, stars on the outer edges of a galactic disk far from the central mass should move slower than those closer in, just as Pluto orbits the Sun much more sluggishly than Mercury. But Rubin's data revealed something astonishing. The stars on the galactic outskirts were moving just as fast as those near the center. The galaxies were rotating so swiftly that they should have flown apart, tearing themselves to shreds. The only possible explanation was that each galaxy was embedded within a massive, invisible halo of something, a form of matter that does not emit, absorb, or reflect any light, yet whose immense gravitational pull was the only thing keeping the stars from flying off into the void. This was the first solid evidence of dark matter's grip. We now know these halos are not just a thin coating. They are the true skeletons of the cosmos, vast spheres of unseen particles that envelop every galaxy. The glittering stars and glowing gas we see in telescopes are merely the decorative lights strung upon this invisible framework. Without dark matter's gravitational well, the primordial gas from the Big Bang would never have clumped together to form the first galaxies. It dictates the architecture of the universe on the grandest scales. For decades, physicists have been hunting for the particle responsible. Deep underground, in abandoned mines shielded from cosmic rays, sensitive detectors wait for the minuscule tremor of a dark matter particle bumping into an atomic nucleus. At the Large Hadron Collider, scientists smash protons together at nearly the speed of light, hoping to create these elusive particles in the debris. So far, the silence is deafening. Dark matter has not shown itself directly. It reveals its presence only through its ghostly gravity, bending the path of light from distant galaxies in a phenomenon called gravitational lensing and orchestrating the motions of stars. Its continued illusion forces us to ask a radical question. What if we have been imagining dark matter all wrong? What if it is not a single, simple particle, but a whole hidden sector of physics, with its own rich complexity and forces that barely interact with our familiar world? We are surrounded by an ocean of the unknown, a shadow universe that forms the bedrock of everything we see, and we have only just begun to sense its tides. Every rule we think the universe follows seems to break down at the edge of a black hole. These gravitational monsters are not just cosmic vacuum cleaners. They are the ultimate paradox, places where our two most successful theories of physics, general relativity and quantum mechanics, meet and declare war on one another. The conflict centers on a seemingly simple question: what happens to information that falls into a black hole? According to the classical laws of gravity laid out by Einstein, the answer is grimly straightforward. Once something crosses the event horizon, the point of no return, it is lost forever to the outside universe, crushed into a single point of infinite density, the singularity. Its unique identity, whether it was a star, a book, or a person, is utterly erased. But quantum mechanics, the rules governing the very small, has a fundamental and unbreakable law: information cannot be destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. This is the black hole information paradox, a deep crack in the foundation of modern physics. The crisis was ignited by Stephen Hawking. He realized that black holes are not completely black. Due to weird quantum effects near the event horizon, they slowly evaporate, emitting a faint glow of particles now known as Hawking radiation. This was a monumental discovery, but it came with a devastating consequence. Hawking calculated that this radiation is purely random, a featureless thermal fuzz that carries no information about what fell in. When the black hole finally evaporates completely, all the information about everything it ever consumed vanishes from the universe. Poof, gone. This idea that information could be permanently lost was so unsettling that it led to a famous bet between Hawking and fellow physicist John Preskill. For decades, physicists wrestled with this, trying to find a flaw in Hawking's math. How could the universe simply forget? The leading resolution to this paradox is as strange as the problem itself, and it comes from the holographic principle, championed by physicists like Leonard Susskind. This mind-bending idea suggests that all the information about the three-dimensional volume of a black hole is not lost inside, but is instead perfectly encoded on its two-dimensional surface, the event horizon. Imagine the event horizon as a vast cosmic hard drive. Every bit of information about an object falling in is not vaporized, but smeared and stored as incredibly intricate, pixel-like disturbances on this spherical surface. Then, as the black hole emits Hawking radiation, it is not emitting random noise. It is slowly and carefully re-radiating that encoded information back out into the universe, like a scrambled message being broadcast. The information escapes not by traveling out, but by being imprinted on the radiation leaving the horizon. This solution forces us to radically rethink the nature of reality. It suggests that our perception of a three-dimensional world might be a projection, a hologram from a two-dimensional surface at the edge of the universe. The black hole information paradox is more than a technical debate. It is a direct confrontation with the limits of our understanding. Resolving it is not about saving data from a cosmic shredder. It is about finding the single, unified language that describes both the force of gravity and the rules of the quantum world. What does it mean for reality itself if the past is never truly lost, but merely waiting, encoded on the boundary of the void, to be read back into existence? Even as we grapple with cosmic ghosts, our own creations have whispered of hidden forces much closer to home. The Pioneer 10 and 11 spacecraft, humanity's first emissaries to the outer solar system, carried with them a quiet mystery. As they journeyed beyond Jupiter and Saturn, their faint radio signals were tracked with exquisite precision. By measuring the Doppler shift in these signals, scientists could calculate their speed to an almost unimaginable accuracy. And that is when they found it, a tiny, unrelenting deceleration. Both spacecraft were slowing down by a minuscule amount, as if a faint, unseen hand was gently applying the brakes. This was the Pioneer Anomaly, a drift from the predicted path so small it was like measuring a single second over the course of 50 years. Yet it was real, persistent, and utterly unexplained by the known laws of gravity and planetary motion. For decades, this whisper from the void fueled speculation. Was it the signature of dark matter tugging at the probes, a flaw in our understanding of gravity itself? Or perhaps evidence of some new, long-range force acting across the vast emptiness? The mystery deepened with every passing year, a constant, nagging reminder that our maps of the solar system were still incomplete. The solution, when it finally came, was a masterclass in humility. It was not a new force of nature, but the ghost of the spacecraft themselves. The probes were powered by radioactive plutonium, which generated heat. That heat, radiating from the spacecraft's electronics and power systems, was bouncing off the back of their large dish antennas. Each individual photon of heat carried a tiny, tiny amount of momentum. But over the vast, frictionless expanse of space, this constant, one-way push from the spacecraft's own warmth was enough to create the precise, steady deceleration that had baffled physicists for so long. Thermal radiation pressure, a well-known but incredibly subtle effect, was the culprit. The case was largely closed, a triumph of meticulous detective work. Yet some nuances remain, a tiny fraction of the anomaly that the thermal model does not perfectly explain. This serves as a profound lesson. The universe is filled with illusions, and the most seductive mysteries are sometimes born from the most mundane realities. It underscores the incredible precision required for deep space navigation, where a miscalculation the width of an atom per second can send a probe millions of miles off course over a decade. As we send ever more sophisticated craft into the darkness, from the Voyagers to the New Horizons probe that flew past Pluto, we must ask, what other subtle, hidden factors are we still missing? Is the gentle pressure of our own machinery the only ghost in the machine, or are there fainter whispers still, waiting to be heard in the silent data streams from the edge of our own celestial backyard? Deep in the silent stretches between galaxies, a scream echoes. It is a blast of pure energy so intense it outshines a billion suns, yet it lasts for less than the blink of an eye. These are fast radio bursts, the universe's most powerful and most fleeting mysteries. Discovered by accident in 2007, when astronomer Duncan Lorimer was sifting through old pulsar data, these events are now the focus of a frantic cosmic hunt. In a single millisecond, an FRB can release more energy than our sun puts out in 3 days. To achieve that, something truly catastrophic must be happening. The challenge is that they are here and gone in an instant, leaving behind only a ghostly imprint in our radio telescopes, a screech that has traveled across billions of light years. The first major clue came when we realized not all bursts are the same. Some are one-off events, a single, shattering detonation in the dark. Others, bafflingly, repeat. They flash from the same patch of sky, not with any predictable rhythm, but in a seemingly random stutter. This simple distinction splits potential explanations in two. A one-off burst could be the final death cry of a cataclysm, like two ultra-dense neutron stars merging into a black hole in a spectacular collision. But a repeating source cannot be destroyed in its own eruption. It must survive its violent outburst, pointing to an object that can produce these titanic energies again and again. The prime natural suspect is a magnetar, a type of neutron star with a magnetic field so powerful it could strip the information from every credit card on Earth from halfway across the galaxy. The twisting of these unimaginable magnetic fields could potentially snap, releasing a blast of radio waves fitting the profile of an FRB. Yet, even this extreme explanation is stretched to its limits by the sheer raw power of the most energetic bursts we have detected. This has led to more speculative and far more thrilling possibilities. Could these focused, incredibly bright pulses be the result of alien technology? A civilization advanced enough to power interstellar light sails might use similarly powerful beams for communication, or perhaps we are seeing the leakage from some unimaginable piece of cosmic engineering. While this remains a fringe hypothesis, its very plausibility highlights how thoroughly these bursts defy our conventional astrophysics. They are cosmic lighthouses flashing in a fog we cannot penetrate, each one a question written in fire. What kind of engine can switch on and off with such violence? And what does it mean that the universe is filled with these brilliant, transient shouts, most of which fade into silence before we can even turn to look? This fundamental conflict has a name: the Hubble Tension. It is a growing crack in the very foundation of modern cosmology. On one side, we have the pristine baby picture of the universe, the cosmic microwave background mapped by the Planck satellite. By studying the subtle patterns in this ancient light, scientists can calculate what the universe's expansion rate should be today, a value known as the Hubble constant. This is a prediction based on the standard model of cosmology, our best recipe for the universe's ingredients. On the other side, we have our most powerful telescopes, like the Hubble Space Telescope, looking at the local, modern universe. They measure the expansion rate directly by observing how fast galaxies are moving away from us. These two methods, one looking at the infant universe and the other at the adult universe, should agree perfectly. They do not. The numbers are undeniably different. The universe today appears to be expanding faster than the early universe says it should be. This is not a small margin of error. It is a statistically significant discrepancy that has survived years of rechecking and refined measurements. Astronomer Wendy Friedman and her teams have meticulously cross-checked the local measurements using different cosmic mileposts, and the tension only grows stronger. The conflict forces a difficult choice. Either there is a systematic error in one of our most trusted measurement techniques, which seems increasingly unlikely, or our standard model of cosmology is missing something vital. Our cosmic recipe, which includes dark matter and dark energy, might be incomplete. Perhaps dark energy, the mysterious force driving the acceleration, is not constant as we have assumed. What if it evolves over time, growing stronger or changing its properties? Or maybe there is an entirely new particle or field, a previously unknown cosmic component that influenced the early universe and left a ghostly imprint on its present-day expansion. The Hubble tension is more than a technical dispute. It is a direct challenge from the cosmos, a sign that the universe is not following the rules we so confidently wrote for it. What other fundamental assumptions are we about to lose, and what breathtaking new physics is waiting to be discovered in the space between two conflicting numbers? Our solar system does not end with Pluto. Far beyond the last known planet lies a vast frozen frontier, a donut-shaped ring of icy worlds called the Kuiper belt. For years, we pictured this region as a gradually thinning cloud of debris, with smaller and fewer objects the farther out you go. But that picture is wrong. At the very edge of our observational reach, the Kuiper belt does not fade away gently. It falls off a cliff. Surveys using powerful instruments like the Subaru telescope have mapped this distant population, revealing a sudden and dramatic drop in the number of objects beyond about 50 astronomical units, a distance that places it far past the orbit of Neptune. It is as if you were walking through a forest that grows steadily sparser, only to find an abrupt, perfectly clear field beyond a certain invisible line. Our models of solar system formation predict a smooth, tapering distribution of ice and rock left over from the planetary construction process. This sharp edge defies that logic completely. Something has violently sculpted this frontier, cutting off the population of objects as if with a cosmic knife. astronomers like Scott Shepherd point to two compelling possibilities. The first is the gravitational hand of an unseen planet. A massive world several times the size of Earth could be orbiting in the darkness beyond the cliff. Its gravity would act as a shepherd, clearing out a vast swath of space by either ejecting smaller objects or herding them into specific, tight orbits. This hypothetical planet 9 would be the architect of this invisible wall. The other possibility reaches even deeper into the past. Perhaps our Sun had a close encounter with another star in its infancy, a stellar sibling that swung by and stripped away the outer material of our primordial disk before drifting away into the galactic night. This event would have left a permanent scar on the architecture of our system, a fossilized boundary from a long-lost celestial partnership. The Kuiper belt cliff is more than just a curiosity. It is a boundary post for a mystery. It marks the edge of the known solar system and the beginning of a shadowy realm whose rules we are only starting to decipher. What silent sentinel orbits in that darkness, enforcing a law we have yet to understand? At the very heart of our galaxy, there is a light that should not exist. A faint, mysterious glow of gamma rays emanates from the core of the Milky Way, a surplus of high-energy radiation that our telescopes can see but our theories cannot fully explain. This is the galactic center excess, a ghostly shine discovered by the Fermi Gamma Ray Space Telescope. It is not the violent light of a single quasar or the predictable pulse of a known star. Instead, it is a diffuse, pervasive fog of energy that blankets the galactic center, a background hum of power with no clear origin. When astronomers meticulously subtracted all the light from every known source, from pulsars to stellar remnants, from cosmic ray interactions to supernova remnants, this unexplained excess remained stubborn and bright. Its very presence is a question mark written in the universe's most energetic script. The distribution of this glow is as telling as its intensity. It spreads out from the galactic core in a roughly spherical halo, its brightness fading smoothly with distance. This shape is crucial. It does not match the flattened disk of the Milky Way, where most ordinary matter resides. Instead, this spherical haze perfectly matches the predicted distribution of something we know is there but cannot see, the dark matter halo that cocoons our entire galaxy. This is what led theorists like Tracy Slatire to propose a breathtaking possibility. What if we are witnessing dark matter annihilating itself? The idea is that when two hypothetical dark matter particles collide, they could annihilate each other in a flash of energy, producing the very gamma rays we detect. It is a cosmic autopsy, an indirect glimpse into the nature of the universe's most elusive substance. Yet, the universe rarely offers a single, simple answer. A competing theory suggests this excess glow could come from a vast, unseen population of millisecond pulsars. These are the rapidly spinning, ultra-dense corpses of dead stars which can beam out powerful gamma radiation. Thousands of these faint, unresolved objects could together create the illusion of a smooth, diffuse glow. The debate hinges on a subtle dance of data. Does the precise energy spectrum of the gamma rays match the signature expected from dark matter particles, or does it better fit the collective output of pulsars? Current observations tantalize but do not confirm. The galactic center excess is a beacon shining from the most chaotic and densely packed region of our galaxy, a place dominated by a supermassive black hole and immense stellar pressures. It illuminates the limits of our knowledge, forcing us to choose between two profound possibilities. Are we seeing the collective whisper of 1,000 dead stars, or are we watching dark matter, the hidden architecture of the cosmos, revealing itself in flashes of self-destruction at the very center of our galactic home? Even the most chaotic stellar deaths can produce perfect geometry. In the constellation Monoceros, a celestial jewel known as the Red Rectangle Nebula defies the typical cloud-like forms of its cousins. Through the lens of the Hubble Space Telescope, it appears not as a messy cloud, but as a stunningly symmetrical structure, a glowing, bipolar hourglass framed by what looks like a lattice of dark rungs, giving it the distinct appearance of a floating, crimson rectangle. This is not an artist's impression, it is a real object, a cosmic masterpiece of order. At its heart lies a binary star system, two stars locked in a tight orbital dance. It is from this partnership that the nebula's bizarre shape emerges. One of the stars has exhausted its nuclear fuel and is in its final death throes, puffing out its outer layers into space. But these gases do not expand in a simple sphere. Instead, they are funneled into two opposing cones by a thick, dense disk of dust that wraps around the binary pair, a donut-shaped barrier sculpted by the complex interplay of the two stars' gravitational pulls and stellar winds. Astronomer Hans van Winkel and his team have studied this system extensively, piecing together the formation process. They suggest that as gas is ejected from the dying star, it slams into this dense equatorial disk. The collisions create powerful shock waves that heat the gas and force it to find the path of least resistance, which is directly upwards and downwards, away from the plane of the disk. This creates the two opposing lobes, or cones, of the bipolar nebula. The mysterious dark bands that form the rectangular lattice are thought to be waves of dense dust and gas, like ripples in a pond, ejected in a regular rhythm during a specific phase of the star's complex interaction. The result is a natural lighthouse beam of cosmic proportions, a structure so precise it looks engineered. How do stars sculpt such perfect shapes from their own demise? The Red Rectangle Nebula stands as a powerful testament to the hidden order within apparent chaos. It proves that under the right conditions, the universe can construct geometric wonders with the same ease as it creates formless clouds, suggesting that the line between random nature and deliberate design is far thinner than we ever believed. This vast cosmic architecture has a name, the cosmic web. It is the largest structure in existence, a spider's silk of dark matter and galaxies spun across billions of light-years, connecting the great clusters and cities of stars in a single, unified network. We have long known that galaxies are not scattered randomly like salt tossed on a table. They gather into clusters, and those clusters themselves are linked by faint, bridge-like tendrils, while between them stretch the immense, empty voids like the Boötes Void. For decades, this was a theoretical prediction, the expected outcome of gravity acting on the faint ripples of the Big Bang. Dark matter, with its immense gravitational pull, would have collapsed first into this filamentary skeleton, a hidden framework upon which ordinary matter would later condense to form the galaxies we see. Confirming this prediction required a new way of seeing the universe. Astronomers like J. Richard Gott championed the use of massive redshift surveys, projects that meticulously map the three-dimensional positions of millions of galaxies. When you plot those positions, the web emerges from the data, a ghostly architecture of nodes where clusters reside, and the long, delicate filaments that connect them. It is a cosmic subway system on a scale that dwarfs human comprehension. The filaments themselves are not solid threads, but rivers of dark matter flowing along invisible gravitational highways, studded with galaxies like lights on a string. The sheer scale of this structure challenges our very ability to map it. Our most ambitious surveys, like the Sloan Digital Sky Survey, have only charted a local corner of this vast network. It is like trying to map every road, path, and alleyway on Earth by only looking at a single neighborhood. The full complexity of the web, with its subtle tributaries and intersections, remains largely uncharted territory. This cosmic skeleton holds the ultimate secret to dark matter. by studying how galaxies move within these filaments, and by using gravitational lensing to trace the distribution of the unseen mass itself, we can probe the properties of this elusive substance. Does it flow smoothly or is it clumpy? How do its particles interact with each other, if at all? The geometry of the web is a direct imprint of dark matter's nature, a frozen record of how it has behaved since the dawn of time. We are only just beginning to trace the outlines of this universal blueprint, a structure so immense it dictates the fate of every galaxy within it. What fundamental truths about the invisible universe are written into the delicate strands of this cosmic net? The silent geometry of cosmic structures is mirrored by a faint chemical whisper from our nearest planetary neighbor. Mars, a world of rust and dust, is breathing. The Curiosity rover, trundling across the desolate floor of Gale Crater, has repeatedly sniffed out tiny puffs of methane gas in the thin Martian air. These are not constant background levels, but sudden, mysterious spikes where the methane concentration soars to 10 times the normal amount, only to vanish again within hours. On Earth, the vast majority of methane is produced by living organisms, from microbes to livestock, making this simple gas a potential biosignature, a chemical shout of life. But Mars is a master of deception. The methane detections are perplexing not just because of their presence, but because of their fleeting nature. Methane should not last long in the Martian atmosphere. Scientists like Michael Mummer have shown that ultraviolet radiation from the sun should break the gas apart within a few hundred years, and certainly within the few hours observed between a spike and its disappearance. This creates a profound puzzle. Something must be actively producing methane on Mars today, right now, and then something else must be destroying it with astonishing speed. The debate splits into two compelling possibilities. The geological explanation points to serpentinization, a process where certain rocks, like olivine, react with water deep underground, producing methane as a byproduct. This would mean Mars is not geologically dead, but possesses a hidden, active chemistry in its aquifers. The other, more thrilling possibility is a biological one. Subsurface microbes known as methanogens could be thriving in watery pockets deep beneath the frozen soil, metabolizing hydrogen and carbon dioxide and exhaling methane as their waste product. These detections are not random. They follow seasonal patterns, increasing during the Martian summer, which hints at a process triggered by temperature changes, perhaps thawing icy seals that temporarily release trapped gas. The very localization of the spikes suggests the source is small and specific, a tiny vent or a crack in the ground that the rover just happened to drive over. This transforms our view of the red planet from a static, fossilized world into a dynamic, active one. The methane is a ghost in the machine of Mars, a tantalizing clue that the most profound discovery in human history might be waiting not on the surface, but just beneath our feet. Is this the faint chemical signature of a hidden, subterranean biosphere, or merely the breath of a cold, rocky world undergoing processes we have yet to fully understand? Motion itself can conjure ghosts from the void. According to the laws of quantum physics, what you perceive as reality depends entirely on how you are moving. An astronaut floating in the deep quiet of space would see nothing but a perfect, empty vacuum. But if that same astronaut were to fire their engines and accelerate, their detectors would suddenly scream to life, registering a warm bath of particles where there was only nothingness before. This is the Unruh Effect, a startling prediction made by physicist William Unruh that ties the very concept of temperature to acceleration. The faster you accelerate, the warmer this phantom radiation becomes. It is a direct and profound analogy to the Hawking radiation emitted by black holes, where the immense gravitational acceleration at the event horizon performs the same trick, turning empty space into a thermal glow. This idea shatters our classical notion of a vacuum as simply being empty. In quantum field theory, the vacuum is a seething, bubbling sea of potential, filled with virtual particles that flicker in and out of existence too quickly to be directly observed. For the comfortably drifting astronaut, these fluctuations average out to zero, a silent hum of nothing. But for the accelerating observer, their motion through this quantum foam is like holding a net through the water. It catches these virtual particles and drags them into reality, giving them real energy and heat. The implications ripple through our understanding of the cosmos. If an accelerating observer sees particles, who is correct? Is the vacuum truly empty, or is it teeming with life? The Unruh Effect suggests there is no single, privileged answer. Reality is not an absolute stage, but a relative experience, its properties changing based on your state of motion. This challenges the core of what we consider to be real, forcing us to accept that particles are not fundamental entities, but artifacts of our interaction with the underlying quantum fields. Though the temperatures involved are so tiny they have yet to be directly measured in a laboratory, the effect is taken seriously by cosmologists and black hole physicists. It hints that our entire universe, in its accelerated expansion, might be sitting in a low-temperature bath of its own creation, a cosmic warmth born from motion itself. What other fundamental properties of our world are merely illusions, contingent on the path we take through the cosmos? Even our most elegant cosmic structures bear the scars of a violent past. The Sombrero galaxy, with its brilliant core and crisp dust lane, appears as a portrait of serene perfection. Yet deep imaging has torn away this peaceful facade to reveal a hidden truth. A colossal, faint halo of ancient stars envelops the galaxy, stretching millions of light years into the emptiness, a ghostly echo of long-forgotten cataclysms. This halo is not a simple, smooth cloud. It is a sprawling archaeological site, littered with the stellar debris of cannibalized dwarf galaxies and punctuated by dense globular clusters, each one a relic of a separate, violent merger. Astronomer David Martínez Delgado and his team use these faint streams and clusters as a fossil record. By mapping their distribution and motion, they can trace the gravitational influence of the galaxy's dark matter halo, the invisible structure that dictates how these stellar fossils are arranged. The sheer size and complexity of this halo defy simple models of galaxy formation. A galaxy like the Sombrero could not have grown so large and accumulated so many ancient clusters through quiet, isolated evolution. Its majestic appearance is a lie, a beautiful mask over a history of galactic violence. It is the product of a relentless billion-year feast, a series of collisions and absorptions that have built its immense halo star by captured star. What appears to be a tranquil island universe is in fact a cosmic Ouroboros, a serpent forever consuming its own past to sustain its present form. How many other seemingly placid galaxies are hiding similar stories of ancient chaos in their faint, outer light? The pristine conditions of the universe's first minutes should have left a specific chemical fingerprint, a predictable mix of the lightest elements. For hydrogen and helium, the predictions match the ancient starlight almost perfectly. But for lithium, the cosmic ledger does not balance. The oldest stars in our galaxy, the stellar fossils that formed from nearly pure Big Bang material, contain only about 1/3 of the lithium that our most sophisticated models say they should. This is the lithium problem, a quiet but persistent contradiction that points to a fundamental gap in our story of cosmic creation. Cosmologists like Brian Fields have spent decades investigating this shortfall. The equations governing Big Bang nucleosynthesis, the frantic nuclear cooking that occurred when the universe was just 3 minutes old, are exquisitely precise. They tell us exactly how much lithium-7 should have been forged in that primordial fire, yet when we look at the ancient stars, it is simply not there. So where did it go? One possibility is that our understanding of stellar physics is incomplete. Could these ancient stars themselves be destroying the lithium, somehow dragging it from their surfaces down into their searing interiors where it is fused into other elements? While some stellar models show this is possible, it is a difficult process to prove and seems an unlikely solution for every single ancient star we observe. The more thrilling alternative is that we are missing a piece of physics from the universe's first moments. Perhaps an unknown particle, like a relic from supersymmetry, was decaying in the early cosmos, its death throes injecting just enough energy to break apart the fragile lithium nuclei as they formed. Or maybe the primordial radiation field was different, influenced by a process we have not yet considered, altering the delicate nuclear reaction rates that set the cosmic lithium abundance. This is not a minor accounting error. It is a direct challenge to our most foundational model of the universe's origin. The first 3 minutes are supposed to be the simplest, the most well-understood part of cosmic history, governed by straightforward nuclear physics. The lithium problem whispers that even in that initial, brilliant flash, something mysterious was at work. What other subtle fingerprints from the dawn of time have we overlooked, and what hidden actor from the primordial stage is still evading our gaze? The cosmos often builds in chaos, but sometimes it sculpts with the hand of a master jeweler. Drifting through space is a celestial wonder so perfectly formed it seems almost impossible. Hoag's object, named for astronomer Art Hoag, who discovered it in 1950, is a galaxy that defies all common classifications. It is not a spiral with winding arms, nor a simple elliptical blob. It is a near-perfect circle of brilliant young blue stars, a cosmic donut floating in the void, with a separate, older yellow core of stars suspended at its very center. The most unsettling detail is the gap, a profound, dark emptiness that cleanly separates the vibrant outer ring from the inner core. There is no visible bridge of stars, no connecting material to explain how these two distinct parts belong to the same system. It is as if someone placed a stellar pearl inside a diamond ring, a structure of breathtaking symmetry that appears both serene and utterly unnatural. How does such a thing come to be, and how does it hold itself together? The leading theory points to a galactic collision, a violent and ancient event where a smaller galaxy plunged straight through the heart of a larger, disc-shaped one. The gravitational shockwaves from this cosmic bullseye could have rippled outward, triggering a wave of star formation in a perfect circle, while leaving the central core relatively undisturbed. Over billions of years, the stars and gas would have settled into this bizarre, stable configuration. Another possibility is an extreme case of gravitational instability, a resonance within the galaxy's own disk that amplified certain orbits and wiped out others, ultimately shepherding stars into this pristine ring. Yet, no single explanation fully accounts for its isolated perfection. Hoag's object is not just a single oddity. A handful of other ring galaxies have been found, but none display such a flawless, circular form and such a clean detachment. It stands as a monument to the fact that the universe's recipe book has pages we have not yet turned. This is not the messy aftermath of a crash, but a finished sculpture, a stable and enduring form that challenges our narratives of how galaxies live and evolve. What other impossible geometries are waiting in the deep field, reminding us that for every rule we write, the cosmos is ready with a beautiful, silent exception? There is a chill in the oldest light of the universe, a cold spot so vast and profound it seems to stare back at us from the dawn of time. In the constellation Eridanus, the cosmic microwave background, that fossilized glow from the Big Bang, holds a blemish. It is not just a slightly cooler patch, it is a colossal region of space, billions of light years across, that is significantly colder than the surrounding expanse. This is the Eridanus Supervoid, and its existence is a direct challenge to our models of a uniform infant cosmos. The most straightforward explanation is that this cold spot is not a feature of the ancient light itself, but a shadow cast by a later structure. Between us and that primordial glow lies a truly immense void, a region of space with far fewer galaxies and clusters than expected, a cosmic desert even larger than the Boötes Void. As light from the cosmic microwave background travels through such an underdense region, it must climb out of a gravitational well. In an expanding universe dominated by dark energy, this climb saps the light's energy, causing a subtle redshift that we perceive as a drop in temperature. This is the integrated Sachs-Wolf effect, a ghostly fingerprint of a vast emptiness on the oldest light we can see. Yet the sheer size of the required void pushes the limits of what we believe is plausible. Could a random fluctuation in the distribution of matter really produce a void of such staggering scale? This question has led to more radical ideas. Cosmologist Laura Mersini-Houghton has proposed a breathtaking alternative. She suggests the cold spot is not a shadow, but a scar. It could be the imprint of a quantum entanglement between our universe and another before the Big Bang, a cosmic bruise left from a primordial collision or interaction in the multiverse. In this view, the cold spot is a fossil, a direct signal from a realm and a time before time began. The debate is far from settled. Is the Eridanus Supervoid a simple, if extreme, cosmic emptiness, or is it a window into the pre-Big Bang conditions that gave birth to everything we know? The chill we detect is more than just a temperature reading. It is the cold breath of a mystery that questions the very origin of our reality. If a black hole is a cosmic drain from which nothing escapes, then its theoretical twin is a gushing fountain. White holes are the exact time reversed opposites of black holes, a bizarre but valid solution to Einstein's equations of general relativity. Where a black hole's event horizon is a one-way street inward, a white hole's horizon is an exit door that nothing can ever re-enter. Matter and energy can only spew outward in a violent, endless eruption, a cosmic geyser of creation. The mathematics is clear and elegant, yet for all our searching, the sky holds no record of such an object. Physicist Carlo Rovelli and others propose a fascinating possibility. What if a white hole is not a separate object, but the other end of the tunnel? In the realm of quantum gravity, the immense collapse of a star into a black hole could, in theory, rebound into a white hole in a distant part of our universe, or even in another universe entirely. This would form a natural wormhole, a bridge through space-time, though likely an unstable and microscopic one. This idea suggests that the matter a black hole consumes is not lost forever inside a singularity, but is instead transformed and re-emitted elsewhere as a new Big Bang, perhaps giving birth to a baby universe of its own. So why does our cosmos seem filled with drains but no fountains? One reason is timescale. A white hole, by its very nature, would have had to exist since the beginning of time to be seen today, as nothing can fall in to trigger its eruption. Another is stability. They may be inherently unstable, collapsing instantly into black holes the moment any stray matter attempts to cross their threshold. Their existence would force a complete rewrite of our understanding of quantum gravity, revealing a universe where death and rebirth are two sides of the same cosmic coin. Are white holes merely mathematical ghosts, or are they the secret engines of creation, hiding in plain sight as the very first moments of our own universe's birth? Our planet's history is written in stone and bone, a chronicle of life's triumphs and sudden, brutal endings. The fossil record reveals a grim rhythm, a series of mass extinctions that have scarred Earth roughly every 26 million years. For decades, paleontologists sought a terrestrial cause, a volcanic or climatic cycle to explain this deadly clockwork, but the answer may not lie on Earth at all. It may be written in the stars. Our solar system is not a static island. It moves through the Milky Way on a grand, slow orbit, a journey that takes about 225 million years to complete. This is our galactic year, but this journey is not a smooth cruise. The galaxy is not a flat disk. It is a warped, oscillating plane, and our sun bobs up and down through this structure as it orbits. Picture a carousel horse not just spinning in a circle, but also rising and falling on its pole. According to the hypothesis championed by scientists like Michael Rampino, every 26 million years or so, this bobbing motion carries our solar system through the densest part of the galactic plane. This is the most crowded and dangerous neighborhood in our celestial city. Here, the gravitational tides are stronger, and the solar system's vast, distant cloud of icy comets, the Oort cloud, is violently disturbed. It is as if we are periodically kicking a cosmic hornet's nest. This gravitational jostling sends a shower of comets hurtling inward, a celestial storm that can last for millions of years, dramatically increasing the odds of a catastrophic impact. The evidence is chillingly correlative. The timing of several major extinction events, including the one that wiped out the dinosaurs, aligns suspiciously well with these predicted passages through the galactic mid-plane. It is a cycle of cosmic violence, a pulse that connects the fate of every living thing on our planet to the grand, mechanical motion of our galaxy. This idea shatters the comforting illusion of Earth's isolation. We are not passive observers of the cosmos, safe in our little bubble. We are passengers on a galactic roller coaster, subject to gravitational rhythms that operate on timescales far beyond human comprehension. Our biological destiny may be intertwined with the dance of the Milky Way, a reminder that the universe's influence reaches down from the galactic scale to touch the very ground beneath our feet. What other ancient scars on our world were inflicted not from within, but from the silent, cyclical mechanics of the galaxy itself? The force accelerating the cosmos might be getting stronger. For decades, we have pictured dark energy as a constant, an immutable force woven into the fabric of space itself, a concept Einstein once called his greatest blunder. This idea, the cosmological constant, has been the bedrock of our standard model of the universe, but new measurements are pulling at that foundation, suggesting dark energy is not a steady pressure but a dynamic entity, one that could be evolving over time. We probe its nature not by seeing it directly, but by watching its effect on the universe's expansion history. Two key methods act as our cosmic detectives. The first involves Type 1, a supernova, those standard candles that first revealed cosmic acceleration. By comparing the brightness of these exploding stars at different distances, we map how quickly the universe was stretching in the past versus today. The second method uses Barrian acoustic oscillations, the frozen imprint of sound waves from the early universe that act as a cosmic ruler. By measuring the apparent size of these imprints at different cosmic epochs, we get another independent measure of how expansion has changed. When cosmologists like Adam Rees and his teams combine these datasets, a tantalizing, though not yet definitive, signal emerges. The acceleration we see today does not perfectly match the story told by the infant universe. It is as if the engine driving cosmic expansion was idling at one speed in the past and has since subtly pressed down on the accelerator. This very idea could be the key to resolving the Hubble tension. If dark energy's strength has increased over billions of years, it would naturally lead to a faster expansion rate today than what is predicted from the pristine early universe alone. A dynamic dark energy would shatter the elegant simplicity of the cosmological constant. Instead of a uniform vacuum energy, we might be dealing with a cosmic field that changes its properties, a quintessence that weakens or strengthens as the universe ages. This would mean the fate of the cosmos is not sealed. The ultimate destiny of everything, a final big rip or a slow, cold fade, could still be written by a force we are only beginning to measure. Is the emptiness of space itself alive with a changing energy, and are we just now learning to read its pulse? This geometric perfection is not carved in rock but spun from clouds. At Saturn's North Pole, a storm of almost impossible symmetry rages, a hexagon with sides longer than the entire diameter of our planet. It is a colossal figure, a six-sided wave pattern etched into the atmosphere, so vast it could swallow two Earths side by side. First glimpsed by the Voyager probes decades ago and later studied in stunning detail by the Cassini spacecraft, this structure has persisted for decades, a permanent feature on a gas giant whose other weather systems are famously chaotic and transient. It is a puzzle of stability, a shape that nature seems to avoid everywhere else. Planetary scientists like Kevin Baines see it as a natural laboratory, a giant experiment in fluid dynamics playing out on a cosmic scale. The forces that maintain this form are a delicate balance between Saturn's furious rotation and its churning atmospheric jet streams. The planet spins so quickly that its day is only about 10.5 hours long, creating immense Coriolis forces that whip the atmosphere into organized bands. The hexagon is thought to be a standing wave, a stable pattern that emerges where a fast-moving jet stream shears against slower surrounding atmosphere, much like a street curving around a central plaza. But why a hexagon and not a pentagon or an octagon? The precise physics remains elusive, suggesting that the specific depth and speed of Saturn's internal winds create conditions ripe for this six-sided harmonic. This is not a rigid structure like a crystal, but a flowing, dynamic river of air, a whirlwind so perfectly tuned it holds its shape for generations. It defies the very nature of storms, which we expect to be messy and short-lived. How does a turbulent, gaseous world lock a perfect geometric shape into its sky for 40 years? And what does that tell us about the hidden currents flowing deep within this ringed giant? Beyond the scattered ice worlds at the solar system's edge, a ghost is pulling the strings. The orbits of the most distant known objects are not random. They are clustered, their elliptical paths mysteriously aligned as if an unseen shepherd is herding them. This gravitational whisper is the core of the Planet 9 hypothesis, a bold prediction that a massive world, up to 10 times the mass of Earth, orbits in the frozen darkness far beyond Pluto. Astronomers Konstantin Batygin and Michael Brown did not set out to find a new planet. They were trying to solve a puzzle: why the orbits of these extreme trans-Neptunian objects were grouped together in a way that defied the gravitational influence of the known giant planets. Their computer simulations revealed that only one thing could consistently produce this strange orbital architecture: the steady, distant tug of a super-Earth on a wildly elongated path around the Sun. This hypothetical planet would trace an orbit so vast that a single year there could last 20,000 Earth years. Its gravitational influence would act like a slow, deep drumbeat, resonating over billions of years to sculpt the paths of these smaller ice dwarfs, pushing their orbits into the peculiar alignment we detect. The hunt for this phantom world is a monumental challenge. Its predicted distance makes it incredibly faint, a speck of frozen sunlight lost in a sea of stars. Astronomers are scanning the sky with the most powerful telescopes, searching for that one slow-moving dot of light against the fixed background of the galaxy. Its discovery would be a triumph of theoretical prediction, but it would also force a profound rewrite of our solar system's history. How could a planet so large form so far from the Sun? It may have been a core of a gas giant ejected early in the solar system's violent youth, only to be captured in a distant, stable orbit by the gravitational influence of a passing star. Or its existence might point to a more exotic origin, perhaps even a rogue planet captured from interstellar space by our Sun's gravity. The possibility of a hidden giant in our own cosmic backyard reminds us that our maps are still unfinished. What other ancient architects are hiding in the perpetual twilight, their silent gravity still dictating the dance of the outer solar system? Our own Milky Way is a cosmic predator. Its serene spiral arms and glowing core mask a violent history of consumption, a story written in the faint, ghostly rivers of stars that flow around it. These are stellar streams, the final remnants of dwarf galaxies that ventured too close and were torn apart by our galaxy's immense gravity. Like tendrils of cosmic smoke, they trace the orbits of their destruction, wrapping around the galaxy in great loops that can take billions of years to complete. Astronomer Amina Helmi has pioneered the use of these stellar fossils, meticulously mapping their positions and motions to perform a kind of galactic archaeology. By reading the chemical signatures and velocities of these stars, she and her team can identify which ones are strangers, pinpointing their origin to specific, long-vanished galaxies. One of the most famous of these relics is the Gaia sausage, the shredded remains of a galaxy that collided with the Milky Way in its youth, an event that may have fundamentally shaped our galaxy's thick disk and inner halo. The process is a slow, gravitational torture called tidal disruption. As a smaller galaxy is pulled in, the difference in gravity between the side closest to the Milky Way and the side farthest away stretches it like cosmic taffy. Stars are ripped from their orbits, forming long leading and trailing streams that eventually disperse, their stars becoming anonymous members of the galaxy's diffuse halo. This is not a rare event. Sophisticated computer simulations show that a galaxy like ours grows through a continuous cycle of cannibalism, absorbing dozens or even hundreds of smaller companions over its lifetime. The Large and Small Magellanic Clouds, the two most prominent dwarf galaxies visible in our southern sky, are currently being devoured, their own gas and stars being slowly siphoned away into a vast gaseous stream. This reality shatters the classic image of galaxies as lonely island universes. They are dynamic ecosystems where the large consume the small in a dance that has continued since the first structures formed. Every star in the halo tells a story of a different homeland, a different creation, now merged into our own. How many distinct galactic voices are singing in the choir of the Milky Way's halo, their original melodies blended into a single cosmic hum? Even the smooth, predictable stage of space-time, as described by Einstein, may be an illusion. At the very smallest conceivable scale, a level so tiny it defies direct observation, the fabric of the cosmos might be a seething, turbulent froth. This is the quantum foam, a concept championed by physicist John Wheeler. Imagine the calm surface of an ocean, a perfect representation of smooth, continuous space. Now zoom in until you see the individual water molecules, a chaotic and frenetic dance of creation and destruction. At the Planck scale, a distance of 10 to the negative 35 meters, space and time themselves are thought to be subject to these violent quantum fluctuations. The very geometry of reality is not fixed but constantly warping, with microscopic wormholes and baby universes bubbling in and out of existence in a frantic, probabilistic dance. This foam is not made of matter but of space-time itself, a granular and discontinuous structure that challenges the core assumption of general relativity, which treats space as a smooth, unbroken continuum. How could we ever detect such an ephemeral, microscopic chaos? The key might lie in the very fast and the very energetic. When a high-energy photon, like a cosmic ray particle, travels across the universe, it is not sailing on a perfectly smooth sea. Theoretically, the bumpy texture of the quantum foam would cause slight variations in its speed. Different wavelengths of light, rattled by the foam, might arrive at our telescopes at infinitesimally different times after a billion-year journey. Similarly, the ripples of gravitational waves from colliding black holes could carry faint imprints of this turbulent substrate, a subtle jitter in the signal that betrays the rough road they traveled. So far, our instruments are not sensitive enough to catch this whisper, but the quest continues. The existence of quantum foam would force a profound revision of our reality. It suggests that the cosmic stage upon which all events play out is not a fundamental bedrock, but an emergent property, an average of countless frenzied fluctuations. What does it mean for our understanding of cause and effect, of here and there, if the very fabric of distance and duration is built upon a foundation of chaos? Deep within the heart of a dying giant, a secret engine ticks away. A Thorn-Zitkow object is a stellar Russian nesting doll, a cosmic chimera where a super-dense neutron star orbits not around, but inside the vast, tenuous atmosphere of a red supergiant. Picture a single neutron star, the crushed core of a once mighty sun now compressed into a city-sized sphere, spiraling inward through the outer layers of its bloated companion until it comes to rest at the very center. There, it no longer orbits, it becomes the heart of the beast. This bizarre hybrid was first envisioned by physicists Kip Thorne and Anna Zitkow, a theoretical possibility born from the complex dance of binary stars. In a close pair, one star explodes as a supernova, leaving behind its neutron star core. If the blast does not kick the system apart, the remaining giant star can swell to engulf its dead companion, which then spirals down, dragging its immense gravity through the stellar envelope. The result is a star that looks ordinary from the outside, a cool, red giant, but harbors a furious, ultra-dense engine in its core. This hidden heart would dramatically alter the star's internal physics. The intense heat and pressure from the neutron star's surface would trigger exotic nuclear reactions deep within the giant's belly, forging rare heavy elements in a process unlike any other in the universe. This unique chemical signature is the ghost in the machine, the only way we could ever hope to identify such an object. Astronomers search for these stellar ghosts by looking for the telltale chemical fingerprints in a star's spectrum, an overabundance of specific elements like rubidium, lithium, and molybdenum that are the byproducts of this extreme internal environment. For decades, the search seemed to yield only dead ends until a candidate known as HV2112 in the Small Magellanic Cloud was identified. Its atmosphere showed precisely the strange chemical cocktail predicted by the models. The discovery sent a ripple of excitement through the community, a potential first glimpse of a star within a star. Yet the universe is a master of ambiguity. Further analysis suggested other, more conventional explanations could also account for the star's peculiar chemistry. The candidate remains just that, a candidate, its true nature still veiled. The hunt continues, a meticulous sifting of starlight for the subtle, radioactive glow of a hidden core. If one is ever confirmed, it would be more than just a new class of star. It would be a direct window into the most violent and intimate phases of stellar evolution, revealing a pathway so extreme it blurs the line between two of the cosmos's most dramatic endpoints. How many of these stellar ghosts are hiding in our galactic backyard, their true identities masked by the placid glow of a giant surface, waiting for us to learn how to read their secret language? Even our deepest views of the cosmos leave a hidden residue of light. When astronomers subtract the glow of every known star and galaxy, a faint, diffuse fog remains, a cosmic infrared background that permeates all of space. This is not the light of individual objects, but the combined whisper of countless ancient sources, a collective glow from the universe's first epochs. Space telescopes like Spitzer and Hubble have mapped this subtle radiance, and it holds a profound surprise. The total amount of this infrared light is significantly brighter than the sum of all the galaxies we can see. It is as if you counted every visible light bulb in a vast city at night, only to find that the total glow was far greater, hinting at a hidden population of lights you cannot directly spot. Astronomer Alexander Kashlinsky and his team meticulously study the fluctuations in this background, the fine-grained texture of its glow. These tiny, pixel-to-pixel variations are the crucial clue. They are not random noise, but a fossilized imprint of the very first structures to ever switch on in the cosmos. The simplest explanation is that we are seeing the collective output of the very first stars and galaxies, population 3 stars, which formed from pristine hydrogen and helium and burned ferociously bright and fast. Their direct light has been stretched by the expansion of the universe over billions of years, shifting from visible ultraviolet into the infrared we detect today. But the sheer intensity of the glow suggests something more. Could there be an entire lost generation of early galaxies, too faint and distant for our current telescopes to resolve individually? Or does this excess light point to more exotic processes, perhaps from the violent accretion of material onto the universe's first supermassive black holes, whose brilliance is now smeared into this uniform background haze? This cosmic infrared background is the ultimate palimpsest, a layered document where the signatures of the first luminous objects are overwritten and blended together. It challenges the completeness of our cosmic census, forcing us to ask what legions of primordial objects remain hidden, their combined glow reaching us as a single, ghostly shout from the dawn of time. The universe has a heartbeat. It is not a sound you can hear, but a vibration you can feel in the very fabric of space-time, a low-frequency hum that resonates through everything. This is the gravitational wave background, a cosmic chorus of ripples left by the most violent and massive events in existence. For decades, gravitational waves were a theoretical prediction, the final piece of Einstein's general relativity to be confirmed. We first detected the loud, singular chirps from pairs of stellar mass black holes colliding. But this new discovery is different. It is not a single event, it is a background rumble, a stochastic signal like the static hiss of a radio tuned between stations, but each pop and crackle is the echo of a distant cosmic catastrophe. This hum is so faint that detecting it required a telescope of galactic proportions. Scientists with collaborations like Nanograv did not build a single instrument. They turned the galaxy itself into one. They used pulsars, the rapidly spinning corpses of dead stars that beam radio waves with the precision of atomic clocks. By monitoring an array of these cosmic lighthouses for over a decade, they looked for incredibly subtle variations in the timing of their pulses. As a gravitational wave passes between us and a pulsar, it minutely stretches and squeezes the space in between, causing the pulse to arrive a few billionths of a second early or late. By correlating the timing drifts from dozens of these pulsars across the sky, they finally teased out the signature of the background hum. This universal vibration is thought to be generated by the collective dance of supermassive black holes. Every large galaxy is believed to harbor one of these monsters in its core. When galaxies merge, their central black holes eventually spiral toward each other, orbiting for millions of years before a final, violent collision. Each of these binary pairs sends out gravitational waves, and the combined signal from every such pair in the universe creates this perpetual, low-frequency ripple. It is the sound of the cosmic web shaking, the vibration of structure itself. Yet there is another, more exotic possibility. Some of this signal could come from cosmic strings, hypothetical defects in the fabric of reality, one-dimensional cracks left over from the universe's superheated birth. If they exist, their snapping vibrations would send powerful waves cascading through space-time. Listening to this hum is like putting a stethoscope to the chest of the cosmos. As the maps of this background grow more precise, they will reveal the population of supermassive black holes throughout cosmic history and could unveil entirely new physics from the universe's first moments. What other secrets are encoded in this universal tremor, a vibration that has been silently passing through us all along? A simple question reveals a profound truth about the cosmos. Why is the night sky dark? If the universe is infinite and filled with an endless number of stars, then every single line of sight from Earth should eventually land on a star's surface. The entire night sky should be a solid, blinding sheet of light, as bright as the surface of the sun. This is Olbers Paradox, named for the German astronomer Heinrich Olbers, who formalized it in the 19th century, though the question is much older. The darkness we take for granted is, in fact, one of the most important clues to the universe's true nature. The resolution lies in shattering two core assumptions. First, the universe is not infinitely old. It has a birthday. The Big Bang occurred roughly 13.8 billion years ago, which means the light from stars beyond that cosmic horizon has not had time to reach us. We live within a sphere of observable reality, and beyond its edge, the light has simply not arrived. Second, and just as crucial, the universe is expanding. This continuous stretching of space itself has a dramatic effect on the light traveling through it. The energy of photons from the most distant galaxies is diluted, stretched to longer, redder wavelengths, and for the very earliest light, right out of the visible spectrum and into the invisible infrared. This is cosmological redshift, and it systematically steals energy from the ancient starlight, rendering it invisible to our eyes. The expansion effectively creates darkness from what should be infinite light. Yet the paradox prompts an even deeper inquiry. What if we could see all the light that has ever been emitted since the beginning? If we could convert every photon from the first stars to the glow of all galaxies into a single image, what would we see? The answer is astonishing. The entire sky would glow with the temperature of a warm spring day, not with the brilliance of a sun, but with a uniform, mild warmth. This is the cosmic infrared background, the combined energy of all creation, faded and cooled by expansion into a perpetual, universal twilight. The darkness above is not an emptiness. It is a testament to a universe with a beginning and a constant, dynamic growth. It is the signature of a cosmos that is finite in time, forever expanding, and hiding its brightest secrets in plain sight. This profound silence from the cosmos might not be an absence of life, but a deliberate choice. We call this the zoo hypothesis, a startling answer to the famous question posed by physicist Enrico Fermi. If the universe is so vast and so old, he asked, then where is everybody? The silence is deafening, but what if that silence is the message? Astronomer John Ball formally proposed this idea, suggesting that advanced extraterrestrial civilizations are fully aware of us, but have chosen a policy of non-interference. They are not hiding from us, they are observing us, much like we observe animals in a protected wildlife preserve. In this view, Earth is a designated planetarium, and humanity is the exhibit. The hypothesis flips the script on our expectations of galactic conquest. We often imagine expansionist empires driven to colonize every star, a vision that makes our lonely planet seem like a failure to be noticed. But a truly advanced intelligence might operate under a completely different ethical framework. Their prime directive might be to avoid contaminating developing cultures, allowing civilizations to find their own path, to make their own mistakes and discoveries without outside influence. This would explain why our sky is not filled with alien advertisements or the traffic of interstellar commerce. It would explain why our radio telescopes hear only natural static, and why no grand artifacts orbit our sun. The universe appears natural because it is being kept that way for our benefit, or perhaps for our study. The zoo hypothesis forces us to confront a humbling possibility. Our technological adolescence, our global conflicts, our entire history, might be a form of cosmic entertainment or a priceless anthropological record for beings so far beyond us that we cannot even comprehend their motives. Are we living in a galactic sanctuary, surrounded by invisible fences made of principle and advanced technology? The unsettling beauty of this idea is that it is utterly untestable with our current understanding. Any evidence we could possibly find would, by the hypothesis's own rules, be hidden from us. We are left to wonder if the greatest discovery we could ever make is that we were never meant to find anything at all. Perhaps the silence is not a choice but a graveyard. The sheer scale of the cosmos suggests a universe teeming with life, yet we find only an eerie quiet, a void where the galactic chorus should be. This contradiction is the heart of the Fermi Paradox, and one of its most chilling solutions is the Great Filter. The idea, sharpened by economist Robin Hanson, suggests that the path from non-life to a spacefaring civilization is not a gentle slope, but a treacherous mountain pass littered with cliffs. At some critical stage, a barrier arises that is almost impossible to cross. This filter eliminates nearly every potential civilization before it can make its presence known across the stars. The true terror of this concept lies in its timing. Is the Great Filter behind us a hurdle we somehow miraculously cleared, or does it still lie ahead, waiting in our future? If the filter is in our past, it could have been the near-miraculous jump from chemistry to biology, the moment non-living molecules first assembled into a self-replicating cell. Perhaps it was the evolution of complex eukaryotic cells, a fluke of symbiosis that took billions of years to occur on Earth. We might be the impossibly lucky ones, the sole winners of a cosmic lottery that eliminated every other competitor. But the more haunting possibility is that the filter awaits us. The same technological intelligence that allows us to ponder the stars could contain the seeds of our own destruction. Nuclear annihilation, a genetically engineered pandemic, or an artificial intelligence that turns on its creators could be the universal bottleneck. Every civilization, upon reaching a certain technological adolescence, invents the tools of its own eradication. The silence we hear is the sound of countless other civilizations that reached this precipice and then vanished. This idea reframes our entire existence. Our current global crises are not just political or environmental problems, they are a test. We are navigating the very phase that may have ended every other intelligent species. The Great Filter forces a profound and unsettling question about our own trajectory. Are we the exception, the rare success story, or are we merely next in a long line of failures, blissfully unaware of the cliff we are rapidly approaching? The Earth itself seems to breathe. While we scan the cosmos for intelligent signals, our own planet presents a different kind of mystery, one where life is not just a passenger, but an active participant in a grand, self-regulating system. This is the Gaia Hypothesis, a provocative idea put forward by scientist James Lovelock and microbiologist Lynn Margulies. They proposed that the entire biosphere, the thin, living skin of our world, acts like a single, vast organism. It does not simply adapt to the environment. It actively regulates and maintains the conditions necessary for its own survival. The planet's atmosphere, its oceans, and its geology are not just a stage for life, they are part of the living performance itself. For instance, Earth's atmosphere is wildly unstable. It is filled with reactive gases like oxygen and methane that should quickly burn out and leave a dead, inert balance. Yet for billions of years, these gases have remained in a precise, life-friendly mixture. Lovelock argued this is no accident. He saw it as evidence of a planetary-scale control system, where life itself tweaks the global thermostat. Microbes in the ocean release gases that seed clouds, algae regulate carbon dioxide levels, and the weathering of rocks by organisms pulls greenhouse gases from the air. All these processes, they suggested, are part of a complex, self-correcting feedback loop that keeps the planet habitable. The idea was met with fierce controversy. To many scientists, it sounded less like a hypothesis and more like a mystical claim that the Earth is a conscious being. They argued it implied a purposefulness that evolution could not provide. How could trillions of unthinking organisms coordinate to achieve a global goal? The debate forced a profound rethinking of our place in the cosmos. The true power of the Gaia concept is not in proving the Earth is a literal goddess, but in revealing the deep, inextricable connections between life and its planet. It defies the simple geophysical models where life is a passive recipient of planetary conditions. Instead, we see a constant, dynamic dance of co-evolution. Life changes the planet, and the changed planet guides the future of life. This perspective transforms a barren rock into a living, breathing entity in a cosmic sense. It suggests that a planet with life is fundamentally different from one without, not just in its chemistry, but in its very behavior. Is the stability of our climate over eons a miraculous fluke, or is it the signature of a biosphere that has learned to manage its own home? As we search for life on distant worlds, perhaps we should not just look for single signs, but for the subtle evidence of an entire world holding its breath in a delicate, self-made balance. The universe you know may be a single page in an infinite book. This is the multiverse hypothesis, a framework where our entire cosmic history is just one iteration in a vast, perhaps endless collection of realities. The idea emerges not from wild speculation, but from the edges of our most successful physical theories. Eternal inflation suggests that the rapid expansion of space that defined our Big Bang never truly stopped, but instead continues in a larger background reality, sporadically spawning new bubble universes like ours, each with its own unique properties. String theory adds another layer, proposing a landscape of mind-bogglingly numerous possible vacuum states, each one representing a different universe with different fundamental constants and laws. Physicist Max Tegmark has attempted to bring order to this dizzying concept by categorizing these parallel realities into distinct levels. The first level is simply a consequence of infinite space. If the cosmos is truly endless, then every possible configuration of matter must repeat somewhere, meaning there are distant regions where every version of you is living out every possible life. The second level consists of those bubble universes from eternal inflation, each with its own separate Big Bang and perhaps even different physical dimensions. The third is the many worlds interpretation of quantum mechanics, where every quantum decision branches reality into a new timeline, creating an ever-expanding tree of possibilities. The fourth and most abstract level encompasses all possible mathematical structures, suggesting that every coherent set of mathematical laws describes a real, physical universe somewhere. This radical idea directly challenges the uniqueness of our existence, the delicate fine-tuning of our universe, the precise constants that allow for stars, planets, and life, may not be a miraculous coincidence, but a simple selection effect. We find ourselves in a universe that can support us, but countless other barren, incompatible realities may exist where physics is hostile to any complex structure. The multiverse forces us to confront a humbling possibility. The laws we consider fundamental and immutable might be nothing more than local bylaws, valid only in our own cosmic neighborhood. Are we living in the only reality, or is every choice you have ever made, and every choice you did not, playing out in an infinite ensemble of worlds just beyond the reach of observation? The most unsettling thought experiment does not require a telescope. It suggests that you and everything you perceive might be a momentary accident. This is the paradox of the Boltzmann brain, a ghost born from the cold equations of statistical mechanics. In an infinitely old or vastly large universe, the random jostling of particles in the void makes anything possible, no matter how improbable. Given enough time, the atoms in a perfect vacuum could spontaneously arrange themselves into a fully formed, self-aware brain, complete with a lifetime of fabricated memories. It would blink into existence, convinced of a past that never was, and then, a moment later, dissolve back into the chaos from which it came. The physicist Ludwig Boltzmann laid the groundwork for this chilling idea by showing that even the most ordered systems can arise from random fluctuations. The paradox emerges when we apply this logic to our own existence. If the universe is truly random over immense scales, then a single, isolated brain with your exact memories is statistically far more likely to form by chance than an entire, coherent, 13.8 billion-year-old universe with galaxies, planets, and a continuous evolutionary history. The simpler fluctuation is the brain alone, not the cosmos that seemingly contains it. This is not a scientific theory to be tested, but a philosophical hall of mirrors that challenges the very foundation of empirical knowledge. How could you ever prove you are not a Boltzmann brain? Any evidence you examine, any memory you recall, any scientific data you point to, could have been conjured as part of the fluctuation. The book you are holding, the sky above you, the very sense of a linear past, all could be an intricate, instantaneous illusion. The universe's apparent age and vastness would be part of the deception, a detailed backstory for a consciousness that is only a second old. This thought experiment defies our intuitive understanding of consciousness and reality, pushing the logic of probability to a terrifying extreme. It forces us to confront a humbling possibility. Our deepest certainty, the reality of our own experience and the world we inhabit, could be the most profound and fleeting of cosmic mirages. Are we the enduring product of a long and structured cosmic evolution, or are we just a flicker of thought in an endless, mindless dark? The nature of reality itself may be the ultimate cosmic secret. A growing number of philosophers and technologists are seriously considering a possibility that sounds like science fiction, the simulation hypothesis. Popularized by Nick Bostrom of Oxford University, this idea suggests that our entire universe, with its galaxies, stars, and the very fabric of our conscious experience, is not base reality, but an extraordinarily sophisticated computer simulation. Think of the most immersive virtual reality game you can imagine, then multiply its complexity by a factor beyond all human comprehension. This is not a claim that we are living in a movie, but a serious argument based on logical extrapolation. The core of Bostrom's reasoning rests on a trilemma, three possibilities. one of which he argues is almost certainly true. First, nearly all civilizations go extinct before reaching a technological level capable of creating such simulations. Second, advanced civilizations have no interest in running simulations of their own ancestral past. Or third, we are almost certainly living in a simulation right now. The logic is as simple as it is unsettling. If even one advanced civilization ever chooses to create many detailed simulations of its history, then the number of simulated minds would vastly outnumber the one original set of biological minds. Therefore, if you are a conscious being, the statistical probability is that you are one of the simulated ones. This idea finds eerie echoes in the quirks of our own physics. The universe appears to run on a set of mathematical rules, a code that can be written down and calculated. Quantum mechanics, with its discrete energy levels and the way particles seem to exist in multiple states until observed, feels strangely like a processor-saving optimization technique, rendering fine details only when necessary to conserve computational resources. The finite speed of light could be seen as a processing limit, a maximum refresh rate for the cosmic simulation. If this is true, it redefines everything. Your memories, your sense of self, the physical world you touch, all could be data structures in a computer built by a being whose nature we cannot even fathom. It challenges the very concept of free will. Are our choices truly our own, or are they the output of a deterministic algorithm running its course? The simulation hypothesis does not offer proof, but it presents a profound philosophical mirror. It forces us to ask what reality really is, and whether the distinction between the simulated and the real even matters if the experience is indistinguishable. Are we the original creators of our destiny, or are we players in the most ambitious game ever coded, unaware of the programmers watching from a reality we may never see? Every generation has looked up and seen a different puzzle. The ancient Greeks charted wandering stars that looped backwards against the fixed constellations, a celestial dance they called retrograde motion. They built intricate models of crystal spheres to explain it, a beautiful fiction that held for centuries. Later, the mystery of nebulous clouds in telescopes sparked debate. Were they distant star systems or nearby clouds of gas? Each of these cosmic riddles, once utterly baffling, eventually surrendered to new tools and new thinking, becoming foundational chapters in our science. The strange backward march of Mars led to the heliocentric model. The fuzzy nebulae were revealed as entire galaxies, expanding the known universe by billions of light years. The bizarre, star-like radio sources called quasars, discovered in the 1960s, were at first incomprehensible until we realized we were seeing the unimaginable light from matter falling into supermassive black holes. Each breakthrough was born from a mystery that refused to fit the established map. The great unknowns of every age have not been roadblocks, but rather the very engines of discovery, forcing us to build better instruments and question deeper assumptions. Our current catalogue of cosmic ghosts, from dark flow to the lithium problem, fits perfectly into this grand tradition. They are the latest set of cracks in our understanding, the places where our most elegant theories meet a stubborn and brilliant reality that does not comply. The true constant in our exploration of the cosmos is not the answers we hold, but the beautiful, humbling presence of the next great question. What will our most confounding puzzles of today, these 40 unseen corners, inspire the next generation to see, to build, and to become? These scattered cosmic puzzles begin to form a pattern when you step back. Each one, from the faint pull of dark flow to the ghostly glow at the galactic center, is a different symptom of the same profound ignorance. We are not facing 40 separate mysteries, but 40 different doors into a single, shadowed room. The first and most persistent thread weaving through them all is the invisible architecture of dark matter. It is the hidden puppeteer behind galaxy rotation, the sculptor of the cosmic web, and the potential source of the gamma-ray excess at the Milky Way's heart. Without its ghostly gravity, the universe would be a formless, expanding mist, incapable of building the structures we see. Yet it remains a silhouette, defined only by the emptiness it leaves in our models. Another common theme is the brutal limit of our perspective. The Great Attractor was hidden behind the dust of our own galaxy. The true nature of the wow signal vanished into the past before we could turn another ear. We are time-bound creatures peering at a universe of unimaginable scales, trying to decipher a cosmic novel by reading only a single, fleeting paragraph. Our very instruments shape what we find, like the pulsar timing arrays that revealed the gravitational wave background only because we learned to use the galaxy as a telescope. This forces a humbling realization: many of our greatest discoveries are not just findings, but admissions of what we cannot see. The influence of scale itself is a recurring character in this drama. Processes that are impossible or fleeting on human scales become the dominant forces of the cosmos. The quantum foam churns at distances a billionth of an atom, while the Fermi Bubbles tower over entire galaxies. A fluctuation that lasts a millisecond, a fast radio burst, can outshine a billion suns. The universe operates on a canvas so vast and a clock so slow that our intuition, forged on a single, temperate planet, is constantly led astray. Recognizing these patterns is more than just cataloging. It is a crucial act of triage for science itself. It tells us where to point our next great observatories and which theoretical paths are most likely to lead to a breakthrough. The quest to understand dark matter now bridges particle physics, astronomy, and cosmology. The search for life's chemical signatures connects planetary scientists with biologists. These anomalies are forcing specialists to speak each other's languages, building a unified front against the unknown. Could a single grand synthesis explain the galactic rush of dark flow, the missing lithium, and the cold spot in the ancient sky? Perhaps these are not separate problems, but different facets of a deeper reality, a theory that seamlessly weaves together the quantum and the cosmic, revealing a universe far more interconnected and far stranger than we have ever allowed ourselves to dream. These 40 cosmic whispers are not dead ends but invitations, each one, from the ghostly tug of the Great Attractor to the chilling possibility that we live in a simulation, has forced us to redraw the map of reality. They prove that the universe is not a static museum, but a living, breathing puzzle box, constantly challenging the limits of our knowledge and imagination. The true value of these mysteries is not in the answers we currently lack, but in the profound curiosity they ignite within us. It is that very drive to understand, to look into the dark and ask a question, that has propelled every great leap in human history. Our journey does not end here, it simply reaches a new vantage point. The cosmos is filled with countless more secrets, each one a potential key to a deeper truth. Which of these discoveries leaves you most awestruck, most baffled, most eager for the next chapter? Let that curiosity be your guide. The universe is speaking in riddles, and the greatest adventure lies in learning.